Question 5 of the 2023 free response is looking at HCl. Now, I know we most of the time think of HCl as an acid, and that's true when it's in aqueous solution, meaning it's dissolved in water, but in its standard state, it's actually a gas. And in question A, we are asked to calculate the moles of HCl gas inside of a container. So we've got some sort of container here, we have a volume, we have a pressure and a temperature, and we have these HCl gas molecules in there. And so looking at the variables I have and knowing that HCl is a gas, I actually know I need to use the ideal gas law, which is PV equals nRT, to find the moles of the HCl. So let's rearrange our ideal gas law to rearrange for moles. So moles will equal PV over RT. We just have to be careful with our units here. Notice how the pressure units are in atmospheres. The volume is in liters. And so when I choose my R constant, which there are a couple of choices depending on the unit, I need to select the R constant that includes atmospheres in its value, which is this one, 0.08. 206 atmosphere liters per mole Kelvin. And we're going to multiply this by the temperature, 296 Kelvin. Okay, and as you can see, atmosphere will cancel out with atmosphere, liters will cancel out with liters, Kelvin will cancel out with Kelvin, and the mole will reciprocal to the top. So in the container, I have 1.84 moles of HCl. All right, and that's how we do the ideal gas law for this problem. Also notice that I've rounded my answer to 3 significant digits because all of these values in the question represent 3 significant digits as well. So my answer will reflect the question. In question 2, in the same container over here, I've cooled down the temperature to 271 kelvins, and we're asked to calculate the new pressure in atmospheres. So there's a couple ways we can do this, but there's a gas law we can use which shows the direct relationship between pressure and temperature of a gas, and that is P1 over T1 equals P2 over T2. Now it makes sense that the pressure will increase when the temperature is high, because higher temperature is going to make those gas molecules move around more, which will make them collide more with each other and with the container. So I know P1 is my 7.45. That's the atmospheric pressure I had in the original scenario. And the T1 was the 296 Kelvin from my original scenario as well. I am being asked to calculate P2, the new pressure, when I've cooled down the temperature to 271 Kelvin. Okay, so if I rearrange this equation, I'm going to have P2 equals 7.45 atmospheres times 271 kelvins divided by 296 Kelvin. Kelvin will cancel out with Kelvin, and my answer will be, to 3 significant digits, 6.82 atmospheres. In question B, it's a sort of a molecular model or a diagram to show what's going on when we dissolve or ionize HCl in water in this aqueous solution. Chloride ions are formed as well as hydroniums, but that's not shown in the diagram. So in the box, we are asked to draw 3 water molecules with the proper orientation around the Cl ion, chloride. Use this to represent water molecules. Well, you guys may remember that in water, so the smaller colored in circles, those are my hydrogens. Hydrogens are my delta positive in my polar water molecule. And then the large circle, this hydrogen is also delta positive. The large circle is my oxygen, that's my delta negative. So it would make sense that when we draw our water molecules surrounding the chloride, we are going to face the positive, delta positive, to this chloride, which is a negatively charged ion. Okay, so we're going to have this ion-dipole interaction where the delta positive of water is going to attract to the delta negative, or actually just the negative of the chloride. Okay, so we'll draw our answer something like this. I don't think you need to label the dipoles or draw these dashed lines. I'm just kind of showing you to walk you through my thought process as to why I'm surrounding the chloride with the hydrogens. And the final question in number 5 is a Ka data table and then another kind of molecular diagram. So we're shown a diagram here, and then we want to explain which acid from this list is represented by this diagram below. So a couple ways we can go about this. First of all, if I write down a kind of a generic equation, HA plus H2O, if I write this in a Bronsted-Lowry kind of equation, we know that acids are H plus donors, so the HA will give away its hydrogen ion to water, creating hydronium, H3O, as well as the conjugate base A minus. So when I look at this equation that I wrote down and I look at this diagram, what I can see in this diagram is that there's lots of HA molecules, which is this one over here. Lots of HA. And I don't have very much hydronium, and I also don't have very much of the conjugate base A minus. So this is my hydronium, and then the conjugate base, this A minus, we only have one of them. So what I know in this question is I mostly have reactant, which means, by the way, remember that Ka equals the concentration of products over the concentration of reactants. In this acid and water we omit because it's a liquid. So the acid that this diagram represents, it must be HNO2, because HNO2 has the lowest Ka value. And when it has a small Ka value, that means you have a low concentration of products, which is your numerator, and a high concentration of reactants, which is your denominator, and it also represents a weak acid, meaning that it did not dissociate very much. It dissociated to a very low degree, okay? So it has the smallest Ka value, indicating it did not dissociate readily and is mostly reactant, which is the HNO2 at equilibrium. All right, and that answers number 5. Please check out the next video if you're interested.